Welcome back. In this video, we're going to be looking at mixed strategy games. So last time we looked at strictly determined games, which are games with a saddle point. And games with a saddle point, each player always chooses the same option, the same row or the same column, because there's always one best solution to the game. In a mixed strategy game, the players are going to vary their strategies. So sometimes they'll pick one row or one column, sometimes they'll pick the other. So let's look at an example. All right, so in this example, we want to find the optimal strategies for A and B and the value of the game. And this is really the only thing we're going to do with mixed strategy games. Every single problem is going to be finding the optimal strategies for A and B and the value of the game. So the nice thing about this unit is it's really just one type of problem. The downside is there's quite a bit of algebra to get the answer, but once you get the process, it works the same every time. All right, so in this example, we have two players, A and B. A is the row player and B is the column player, as usual. Both have two options. So in this game, both players have two cards from a deck of cards, a red card and a black card. Doesn't matter what card it is, just one red card, one black card. So very, very simple game. And they decide to show one card or the other. So in this game, if A and B both show a red card, player A loses $2. If A shows a red card and B shows a black card, then player A wins $3. So that value is positive 3 on our matrix. If A chooses a black card and B chooses a red card, then A loses $1. And then if A chooses a black card and B chooses a black card, A wins $4. So our matrix is -2, 3, -1, 4. All right, so the first thing we want to do before we do anything else is make sure this is a mixed strategy game and not a strictly determined game. Because if it's a strictly determined game, then we already know our answer. It's going to be the saddle point. So let's check. All right, so saddle point is the smallest element in its row and the largest in its column. So let's circle the smallest element in each row. So -2 is the smallest in the first row, -1 is the smallest in the second row. And then we'll underline the largest element in each column. So first column, -1 is the largest. Second column, 4 is the largest. And so we see here that we actually do have a saddle point. -1 is the saddle point. So this is not a mixed strategy game. This is a strictly determined game. So optimal strategy for A. So player A, they are always going to choose black. They're always going to choose the strategy that results in the saddle point. So they're never going to choose red, so that's 0% of the time. And then they're going to choose black 100% of the time, so 1. B's optimal strategy is they're always going to choose red because that's their best option every single time because that results in the saddle point. So they're always going to choose red, so that's 100% of the time. They'll never choose black, so that's 0% of the time. And then our value of the game is the saddle point itself, -1. So that's it. If you've got a saddle point, that's as much work as you have to do to find the optimal strategies and the value of the game. All right, now let's do an example where that doesn't happen. We're still going to start with looking for a saddle point, and you should do that on every problem because if there is a saddle point, it's way easier. All right, so circle smallest in each row. So same example here, two players, show a red card, show a black card. But in this case, our matrix is 1, -3, -2, 4. So that is, if both players choose a red card, A wins $1. If both players choose a black card, A wins $4. If they choose different colors, where A chooses red, B chooses black, A loses $3 or B wins $3. And if A chooses black, B chooses red, then A loses $2, B wins $2. All right. So circle smallest in each row. That's the -3 in the first row, -2 in the second row. And then underline largest in each column. That's going to be the 1 in the first column and the 4 in the second column. So we can see that we do not have a saddle point. So this is going to be a mixed strategy game. And for our mixed strategy games, we're going to be finding 4 expected values. So let's start with the first one. The first expected value we're going to be finding is the expected value for player A given player B chooses a red card. All right, so this is going to seem a little bit backwards. But the reason why is because our expected values for each player are based on what the other player does. So this given B chooses red is really important. So we're finding the expected values for A given what B does. So we're going to set up an expected value table just like we did in the probability unit with our X's and our P's. So if B chooses a red card, which is what we're looking at here, if B chooses a red card, then what we're looking at is a value of possibly 1 or -2, depending on what A chooses. But again, we're looking for the expected value for A given B chooses a red card. All right, now we don't know the probabilities, but that's okay. 1, we know they have to add up to 1 because there's only 2 options. And 2, we can choose either one we want to solve for. So let's say we want to solve for the probability with which A should choose a red card. So that's the value of +1. So I'm going to write that up here, red and black. So the 1 is the value that we get if A chooses a red card. The -2 is what we get if A chooses the black card. So we need to know what this is. So this P1, that goes with red. We could have put P1 under black, and that would have been fine. We would have been solving for the probability with which A should choose the black card. It doesn't matter. Just as long as you remember which one you solved for, that's all that matters. All right, so if player A is going to choose red, P1 percentage or proportion of the time, then they're going to choose black 1 minus that. So 1 minus P1. So if they chose red 2/5 of the time, then they would choose black 3/5 of the time. All right, so now what we're going to do is calculate this expected value. So we multiply down and then add across. So 1 times P1, that's P1. And then -2 times 1 minus P1. We'll just write it like that for now, and then we'll go ahead and distribute. So P1 minus 2, we distribute that -2, so that's going to make it a +2 P1. And then we'll add our like terms. That's going to give us 3 P1 minus 2. So that's our first expected value. So make note of that one. 3 P1 minus 2. That's the expected value for A given B chooses red. All right, so now let's look at our next expected value. Our next expected value is going to be the expected value for A given B chooses black. So if B chooses black, then our possible values, so we'll write another expected value table, X and P. Our 2 values if B chooses a black card are -3 and 4. So again, what's important here is we're given that B chooses a black card. All right, now the -3, that's what the value is if A chooses a red card. Well, earlier we said the probability that A chooses a red card is P1. And then we said the probability that A chooses a black card, that's the 4, that's 1 minus P1. So those stay the same. So again, -3 is if player A chooses a red card. 4 is if A chooses a black card. All right, so we'll do the same thing. We'll multiply down, add across. So -3 times P1, that's -3 P1. And then plus 4 times the quantity 1 minus P1. Once again, we'll distribute. So -3 P1 plus 4 minus 4 P1. And then we'll add our like terms. So that's going to give us -7 P1 plus 4. And that is our second expected value. So again, we're going to do 4 of those. but those are our first two. All right, so why are we finding these expected values? I haven't really explained that yet. And that's because this is kind of where I feel like it makes the most sense. So let's write down our expected values real quick. Let's go to another page. So we found the expected value. Let's go back real quick. We found the expected value for A, given B chooses red. That was 3p1 minus 2. And then we found the expected value for A, given B chooses black. And that was negative 7p1 plus 4. All right, so we had 3p1 minus 2 for our first expected value, and negative 7p1 plus 4. So the whole point of the mixed strategy games is each player essentially wants to remove the other player from the game. They want to make the best decision they can regardless of what the other player does. So think about any card game, any board game, any sport that you've ever played. Think about how good of a strategy it would be if you had a strategy that it didn't matter what the other person did. You already knew what was going to happen before the other player did anything. That's what we're trying to do here. Mathematically, we want to remove the other person's choice, the other player's choice, from the game. And the way we're going to do that is we're going to find the probability with which A should choose each colored card, regardless of what player B does. So we want to have the same outcome if player B chooses a red card as if player B chooses a black card. And so what we're going to do is we're going to set these two expected values equal to one another. That way, the expected value if player B chooses a red card is the exact same as the expected value if B chooses a black card. So we set those equal, and now we're going to solve for P1. Let's add jumped ahead, add 7p1 to both sides, which is going to give us 10p1 over here. So 10p1 minus 2 equals 4. And then let's add 2 to both sides. And that's going to give us 10p1 equals 6. And then we'll divide both sides by 10. We'll get p1 equals 6/10 or 3/5. So what that tells us is that player A should choose the red card 3/5 of the time. So what that means is if player A is going to play this game 5 times, then they should choose the red card 3 of those times. The best choice would be to randomly select which 3 of those times, but their best strategy is to pick the red card 3 out of the 5 times, which also means that they would choose the black card 2 out of the 5 times because that's their only other option. So they're going to choose black 2/5 of the time. So that's the 1 minus P1 part. So A's optimal strategy, we already know, it's 3/5 and 2/5. And we put that in a 1/2 matrix. So that is player A's optimal strategy. 3/5 of the time they're going to play the red card. 2/5 of the time they're going to play the black card. Okay. All right, so now we just need to repeat that process for player B. All right, so now we want to find the expected value for B given A chooses red. All right, so if A chooses red, that's our first row. So notice this seems backwards. The expected values for B, or the expected values for A, were based on what B did. So we were looking at values in the columns. First column, second column. Now that we're looking for the expected values for B, we're looking for the values in the rows. So it seems backwards. So this is one of the most common mistakes I see is people find the wrong expected values. Well, they find the expected values correctly, but for the wrong player. So just remember, anytime we're finding the expected values for a player, those values are based on what the other player does. So B's expected values are based on what A does. So expected value for B, given A chooses a red card. So we'll draw our expected value table, X and P. Our outcomes are either 1 if if B chooses a red card, or -3 if B chooses a black card. All right, now this is not going to be, we already solved for P1. That was the probability with which A should choose the red card. So the probability with which B should choose the red card, let's let that be P2. And again, we could have put that here. We could have put that as the probability with which B chooses the black card. It doesn't matter. You can choose whichever, just as long as you know which you chose. All right, so then if we choose P2 to be the probability with which B chooses a red card, then 1 minus P2, that's going to be the probability with which B should choose the black card. All right, so once again, we'll multiply down. That's P2 minus 3 times the quantity 1 minus P2. And then we will distribute. So that's P2 minus 3 plus 3P2. Since we distribute that negative, that's going to give us 4P2 minus 3. All right, so that is our next expected value. So that's the expected value for B given A chooses a red card. All right, one more expected value. Expected value for B given A chooses the black card. All right, so if A chooses the black card, here are our values. So draw out our expected value table once again, X and P. If A chooses or if B chooses a red card, the value is -2, and if B chooses a black card, the value is 4. So that's red, and that's black. All right, so again, probability with which B should choose a red card, we called that P2, and the probability with which B should choose a black card, 1 minus P2. All right, multiply down, -2P2 plus 4 times the quantity 1 minus P2. All right, we'll distribute -2P2 plus 4 minus 4P2. And that's going to give us -6P2 plus 4. And that's our fourth expected value. So we've got the two expected values for player B. The expected value for B given that A chooses red, that was 4P2 minus 3. And the expected value for B given A chooses black, that was -6P2 plus 4. All right, so 4P2 minus 3 and -6P2 plus 4. So those are our two expected values for player B. Player B wants the same thing as player A. They want to be able to remove player A from the game so that they know what to do no matter what player A does. So we're going to set those expected values equal to one another. All right, we'll add 6P2 to both sides. So that's going to give us 10P2 minus 3 equals 4. And then add 3 to both sides. So we get 10P2 equals 7. And then divide by 10. So we get P2 equals 7/10. So if player B chooses the red card 7/10 of the time, so we'll write that down, 7/10 for the red card, then that means they would choose the black card, of course, 3/10 of the time. That's 1 minus P2. And if they played like that, that would be their best or optimal strategy. So B's optimal strategy is play the red card 7/10 of the time, the black card 3/10 of the time. All right, so what that means is if player B was going to play the game 10 times, they would randomly select 7 of those times to play a red card, 3 of those times to play a black card. All right, so the last thing we want to do is find the value of the game, and that we can do by multiplying our 3 matrices together. So you probably noticed when we wrote the optimal strategy for A, let's go back there, we wrote that as a 1/2 matrix, 3/5 and 2/5. And then when we wrote the optimal strategy for B, we wrote that as a 2x1 matrix, 7/10 and 3/10. The reason why we did that is solely because that's just the way it has to be to multiply the matrices. So when we multiply them like this, that's what we're going to get. So here's A's optimal strategy. Here's M, our payoff matrix, and here's B's optimal strategy. So you can do this in your calculator. So you want to create a matrix for A, a 1x2 matrix, 3/5 and 2/5. A matrix for M, that's our payoff matrix. That was the matrix we started with, 1, -3, -2, 4. And then B's optimal strategy matrix, a 2x1 matrix, 7/10 and 3/10. And if you multiply all those together, what you're going to get is -0.2. That is the value of the game. And it is an expected value. That is the expected value or expected outcome of this game. So what that means, since it's a negative value, remember that the numbers are always in terms of player A. So a negative number means that player A is losing money. So what this would say is that if player A chooses red 3/5 of the time, black 2/5 of the time, and B chooses red 7/10 of the time, and black 3/10 of the time, then on average, we would expect for player A to lose about 20 cents every time the game is played. So -0.2 is -20 cents if this is money. So that is our value of the game. Now, one quick question. What would happen? So that was, I'll go back real quick. A choosing 3/5 and 2/5, B choosing 7/10 and 3/10. What would happen here if A played their optimal strategy, 3/5 and 2/5, but B didn't? So let's say you're player A and you're playing with a young child who just likes the color red. They're going to play red every single time. So they play it 100% of the time, and they choose black none of the time. They just want to play the red card. What's going to happen? Who is this going to be better off for? So in my in-person classes, I usually ask this as a clicker question in class. And I get a lot of different answers. I think people think I'm trying to trick them, which I'm not, because one of the things I've been saying this whole time is that the whole point of this is to remove the other person's strategy from the game. And so what's going to happen here is we get -0.2. B's strategy here does not matter at all. Only one player has to play with their optimal strategy, and we automatically know the outcome of the game, because the strategy for both players was to remove the other person from the game. So B could play any strategy they want. They could choose red half the time, black half the time. They could choose black all of the time, red none of the time. The outcome of the game, or the value of the game, would still be -0.2. So that's kind of the fun part about this, is mathematically we can literally remove the other person from the game. We know the expected outcome regardless of what the other player does. Because of this, we can actually solve for the value of the game earlier in this problem than we actually did here. Because once we know one player's optimal strategies, we already know the value of the game, because it doesn't matter what the other player does. So let's look real quick at the expected values. So here were A's expected values, 3p1 minus 2 and -7p1 plus 4. And just as a reminder, p1 was 3/5. B's expected values, if you remember, were 4p2 minus 3 and -6p2 plus 4, where, whoops, that should be a p2, not a p1, where p2 was 7/10. So if we take each of those values, p1 and p2, and plug those in to any one of these. So if we take P1 and plug it into either one of these expected values, or if we take P2 and we plug it into either of those two expected values, what we're going to get is negative 0.2 every single time. So if we plug 3/5 into 3P1 minus 2, we're going to get negative 0.2. If we plug 3/5 into negative 7P1 plus 4, we're going to get negative 0.2. If we plug 7/10 into P2 for 4P2 minus 3, we get negative 0.2. And if we plug 7/10 into negative 6P2 plus 4, we're going to get negative 0.2. We can find the value of the game at any point once we know one of the probabilities. Because again, the whole point is to remove the other person's strategy from the game. Once one player knows what they should do, the game is set. We know what the expected outcome is going to be. So what I recommend doing here is once you find P1, you can find the value of the game, but it is not a long process to multiply your matrices together. I recommend doing that as well, just so you can double check your answer, make sure you got it all correct. So recap real quick on how we did all this. So first step, as a reminder, we checked for a saddle point. Because if there is a saddle point, we automatically know the outcome of the game. Then we found our 4 expected values. First, expected value for A, given B chose the red card. That's the values in the first column. Expected value for A, given B chooses the black card. That's the second column. We then set those values equal to one another and solved for P1, 3/5. Then we found the expected values for B. Expected value for B given A chooses a red card. That was our first row values. Then we found the expected value for B given A chooses a black card. That was our second row values. And then we set those equal to solve for P2. So we found 2 expected values, the 2 expected values for A, set them equal, found P1. Found the 2 expected values for B, set those equal, found P2. Then we multiplied the values together to get the value of the game. And then, of course, we learned that we could just plug P1 into either P1 expected value or plug P2 into either of the P2 expected values, and we could find the value of the game that way instead. All right, that's how you find the optimal strategies and the value of a game for a mixed strategy problem.